Good afternoon to all. I hope the screen is visible and my voice is audible.
Yes, sir.
Okay. Thank you, Pavan Chandra.
Audible now.
So, I have given a live streaming event also for this session. Those who want to stream it in live or those who want to watch it on live streaming can use this ID. It is given in this chat box. So, they can use that also. And somebody had joined now only. I'll give you an live streaming ID. If you want, you can use it. You can watch, you can chat also using live streaming ID. Okay. So in today's class, we are going to start a fresh new unit. It is unit number 5. So the pending topics of cyclic product codes and quasi product codes, we will discuss that in on 27th of October this month. So 27th October we will have a session on the two topics which is being left out in unit number 4. Why I am rushing into the next unit is that by October 31st we need to complete the whole 5 units syllabus, and in addition to that we'll be having internals on 28th October onwards, second internal test. So hardly I'll be getting only some 4 hours or so which would be left out. So for giving a detailed explanation about unit number 5 would not be sufficient. So I had earmarked that October 27 for cyclic products and quasi products topic of unit number 4, and today we'll start a fresh unit number 5, which we call it as convolutional codes. So let us start the session. Unit 5 is convolutional arithmetic codes, or in general can call it as convolutional codes. So what are the topics that we are going to see in this convolution codes is, the topics might be very simple: encoding of convolution, structural properties and distant properties. But the each and every concept of convolution code is a bit complex to understand, and once if you understand the convolutional codes, it will be very much easier for solving. Okay, so let us start with the definition of convolution codes. So far what are the codes that we had seen is linear block codes and cyclic codes. So apart from that we have another sequential structured system, or the structured sequences, which is another type called convolutional coding. So let us define the convolutional coding first. The convolutional coding is done by mixing or combining the fixed number of input bits. The input bits would be fixed, so depending upon that we'll be doing some operation. So what operation is that? Is your modulo 2 operation. So the input bits would be stored in a fixed lengths, and they will be combined with the help of an operation called modulo 2 operation, which we call it as using exclusive OR get operation. So this operation would be equivalent to binary convolution, so which we call it as convolution coding. So the convolution is a term that you would have been studied in your digital signal processing. Convolution. Maybe you would have studied, or you might be studying in Unit 5, I think so. So convolution. So any operation that uses convolution procedure with modulo 2 addition for a fixed number of input bits. So that particular code we call it as convolution codes. So here is a diagram. You can see a diagram which consists of a message input bit M represented by M, message input bit. So this bit is always the current message bit. This bit is the part of a shift register, always M. So another we have two successive messages, which is M1 and M2. So these M1 and M2 represents the state of the shift registers depending upon the problem. Depending upon the problem, we will be having two flip-flops which would be stored, acting as your shift register. And this modulo 2 addition depends upon the problem being given. We'll be having a single output, and the output will be having two sequences. Since we have two message bits in flip-flops representing the state of a shift register, we'll be having two outputs, which is x1 and x2, as in our G of P, G1 of P and G2 of P in cyclic codes in a similar fashion. So how this x1 is obtained depends upon the problem. How this x2 is obtained depends upon the problem. So in this problem, what we're going to see is that x1 is modulo 2 addition of all the three, M, M1 and M2. Whereas x2 is modulo 2 addition of only M and M2. So this diagram is a convolution encoder for a specific example of capital K is equal to 3, N is equal to 2, and small k is equal to 1. So what are this K? What is this N? What is this small k? We'll see in detail. Okay. So K, small k is the number of message bits. So you can see number of message bits is only 1. You can see here number of message bits is only 1, since only M is the message bit. So small k is 1. Fine. Small k is 1. Next, what is this N? So N is the number of encoded output bits. N is the number of encoded output bits, which is this. So you can see how many output bits are they? We have two output bits, x1 and x2. X1 and x2. So N is equal to 2. So it is number of encoded output bits for one message bit will be N is equal to 2. So how the operation does is that x1 is equal to M, M1, M2 modulo 2 addition, x2, M and M2 modulo 2 addition. Okay. So this is your convolutional encoders diagram. Next is we need to define the code rate. Code rate of this encoder. How do we define code rate? Code rate is your formula that we had seen in linear block codes. It is the same formula, K by N. So for this diagram, or for this problem, the small k value is 1 and n value is 2. So this is the code rate of this convolutional encoder. So 1 by 2 1 by 2. You can see small k is what, small n is 2. So 1 by 2 code rate is this is the code rate for this convolutional coders, specifically convolution encoder. 1 by 2 is the code rate. So what happens in this is that in this convolutional encoder, we observe that whenever a particular message bit enters a shift register, it will remain in the shift register for 3 shifts. You can see that when a message enters in the diagram, when a message enters, when a message input enters here, it will be present in this 3 shift registers. Since we are having M, M1 and M2, so it will remain in the 3. So how it will remain is that in the first shift, message bit will be entering in M. In the second shift, it will be entering in M1. In the third shift, it will be entering in M2. So we have 3 successive shifts for this information to move out of the encoder. So 3 shifts are required. So then we can define the constraint length. Okay. So what is this constraint length is that just now we had said that there are 3 shifts. See here there are 3 shifts. So first shift, second shift, third shift. So how many shifts are there? 3. So the constraint length is 3 bits. So the constraint length of a convolution convolution coder is defined as the number of shifts over a single message bit that can influence the encoder output, which is measured in terms of message bits. So for a single message which is to be shifted, it requires 3 shifts. So the constraint length capital K is 3. So this is why it is written as capital K, which is constraint length 3, small k is equal to 1, and n is equal to 2 in the block diagram, where capital K is constraint length, K is the number of message input bits, n is the number of encoded output bits for 1 bit message. Okay. So next is to write the dimension of the code. So how do we write the dimension of the code is, as we have done for linear block codes and cyclic codes, we need to write n comma k. Okay. So n comma k. So this convolutional encoder is n comma k. So n value is 2, k value small k. We should not take big K, not capital K. It should be small k. So k is equal to 1. So 2 comma 1 is the dimension of this convolutional encoder. Okay. So now okay. So next topic is uh, domain approach analysis of convolutional encoder. How do we analyze this convolutional encoder in time domain? So for this, the same diagram we are going to take, and we are going to denote a sequence G0 of 1, G1 of 1, G2 of 1 till Gm of 1 as the impulse response of the adder that generates x1. So you can see that in the diagram we have two x1 and x2 outputs. So that for this we'll have a generator sequence for x1, and for x2 also we'll have a generator sequence. So for x1, let the impulse response be G naught of 1, G1 of 1, G2 of 1 till Gm of 1. Similarly, for the x2, the impulse response of the adder be G naught of 2, G1 of 2, G2 of 2 till Gm of 2. So these impulse responses that we are writing in terms of G naught of 1 till Gm of 1 and G naught of 2 till Gm of 2 are called as generator sequences of the convolution codes. Are called as the generator sequence of convolutional code. So now let us assume that the incoming message sequence be M0, M1, M2 till MM, for example, and the encoder generates two output sequences X1 and X2, and these are obtained by convolving the generated sequences with the message sequences. Hence, the name convolution code is given to this code. So let us see how do we do this convolution. Okay, G0 and M0. So the convolution can be done by using modulo 2 addition, where x1 can be obtained by xi of 1, which is summation L is equal to 0 to M GL of 1 M of minus 1, where M I minus L I vary from 0 to 0, 1 to till L. Similarly, the sequence of x2 can be obtained as xi of 2, which is equal to summation L is equal to 0 to M GL of 2 M I minus L. So where I varies from 0, 1 to till L. So note that here the additions are done based on modulo 2 addition. Modulo 2 addition. So next, for this sequence of this problem, for this two sequences x1 and x2, which are being used by multiplexed switch, the output sequence of x of I can be given as x naught of 1, x naught of 2, x1 of 1, x1 of 2, x2 of 1, x2 of 2, x3 of 1, x3 of 2 until it goes on. And we can find V1 as xi of L, which is x naught of 1, x1 of 1, x2 of 1, x3 of 1, which is the sequences due to x1 output. And similarly, we can write for V2 is equal to xi of 2, which is x naught of 2, x1 of 2, x2 of 2, x3 of 2 till the last, where this xi is the output of the convolutional encoders. Okay. So let us see all these things with a problem such that you can understand it better. Okay, if you do a problem, we'll be understanding it more. For a convolutional encoder, a diagram is given. A diagram is given. We need to find the dimension. We need to find the code rate, constraint length. Sir. Class தான் சொல்லுங்க சார். சொல்லுங்க கிளாஸ் முடிச்சுட்டு பிஸி ஆயிடுங்க சார். சொல்லுங்க. Yeah, sorry for the interruption. So we'll start the problem from the beginning. So the given problem is that convolutional encoder diagram is given. Okay. So this diagram resembles as same as your diagram as in 3.5.1 which I had shown you. Would be more or less same, I think so. Let us check that. Okay. So we need to determine the following. We need to find the dimension of the code. Keep in mind what is dimension. It is n comma k. We need to find code rate. Remember that it is k by n. Constraint length, which is capital K. Generating sequences or the impulse responses, which is x I of 1 and x I of 2. And then the given question is output sequence for message sequence. We need to find the output for the message sequence M, which has 1 0 0 1 1. So first let us see what the diagram is. So the diagram consists of two flip-flops. You can see there are two flip-flops, flip-flop 1, flip-flop 2. Okay, so these flip-flops represents that they are meant for storage, so which is M1 and M2. Okay, so we can redraw that also. I think so. You can redraw. Okay, don't worry. We'll redraw it. So M1, M2. So flip-flop 1 output is M1, flip-flop 2 output is M2. So keep that. Then you can see, you can observe that there is a message sequence also. Message sequence is your M. So which is this 1 0 0 1 1, which is going to be applied here. So which is given as itself as M. So current message bit is M. So totally we'll have 3 blocks, which is M, M1 and M2, which I'll show in the next slide. So we'll have M, M1, M2. So this is present. Okay. So then from the diagram you can observe that there is two modulo 2 additions. So at the up we have one modulo 2 addition, at the bottom we have one modulo 2 addition, which are connected to an output sequence by two switches, switch 1 and switch 2. So you can see that here in the top top modulo 2 adder we have three inputs. One is M, another one M1, another one M2. So I can redraw it as M, M1 and M2 at the top. Okay, I can redraw like that for determining X1. Then at the bottom we have another modulo 2 adder or modulo 2 addition of M and M2. So then if I redraw, I'll get like this. So we have a message input which is given, and at the current state we have M, M1 and M2 are the shift register flip-flops which are present, and as a result of the diagram given, X1 will be obtained by the modulo 2 addition of M, M1, M2, whereas X2 will be a result of modulo 2 addition of M and M2. So this given question can be redrawn as this diagram. Sorry. So is there any queries till this redrawing structure? If there is any queries, please put in the chat box. Let me know. Let me know about the queries such that I can proceed further. Redrawing into this convolutional encoder. Only when once we understand redrawing it, it will be easier for you. So until we redraw the given structured convolutional encoder, it would be difficult. So redrawing is an important part. So redraw should be known. So is that clear? Shall I proceed? After redrawing, okay, since no queries, I'll move on to the next slide. Okay. So next, after redrawing, I need to find the dimension of this. So how do I find the dimension? Just now I had explained you how many outputs are there? One output. Okay, so keep it as it is. Now see how many message input is there. Message input is only one at a time, or it is one. So k will be equal to 1. So when you give 1, how many outputs we get? Which is x1 and x2. How many x1 and x values are obtained? There are two values. So n will become 2, k will become 1. So dimension of this convolutional encoder is n comma k, which is 2 comma 1. And the code rate formula is r is equal to k by n, which we had seen in the earlier class, or even in linear block code. The formula for finding code rate is k by n. So 1 by 2 is code rate. So we had found dimension of the code rate from redrawing. And easily you can find the constraint length also. So constraint length is 3 shifts. There will be 3 shifts in this problem. So every message bit affects outputs of 3 successive shifts. So hence constraint length capital K is 3. Okay. So we had found the first 3 questions that has been given. So next we need to find generating sequences. Generating sequences. So how do I find this generating sequences? So this generating sequences depends upon the value of I. So this I value is your constraint length. Okay, is your constraint length. So from the diagram, we need to see what is our x of I of 1 or x1. When do we get x1 or x of xi of 1? Is that we get it from modulo to addition of m1, m2. Okay, so we get modulo to addition of m1 and m2 for xi of 1. So x1, that is xi of 1, is generated by adding all the 3 bits, by modulo to addition of all the 3 bits. So the generating sequence can be written as generating sequence for x1 or xi of 1 can be written as 3 ones, 1 1 1. So where the first one represents g0 of 1, representing connection of bit m. Second, g1 of 1 is equal to 1, represents connection of bit with m1. Next, g2 of 1 is equal to 1, represents connection of bit m2. So we get the generating sequence for xi of 1 as 3 ones. Similarly, we can find it for x2 also, which is xi of 2. So xi of 2 is addition of the, you can see, let us see xi of 2. Xi of 2 or x2 is modulo to addition of m and m2. M is the first bit, m2 is the last bit. So in between we don't get it. You can see from the diagram redrawn, x2 is obtained by m modulo to addition m2. M and m2. Okay, so we get x2. So then you can write g0 of 2 as 1, representing connection of bit m. G1 of 2 is equal to 0, representing that m1 is not connected, and g2 of 2 is equal to 1, so representing connection of bit m2. So In sequence, you can write gi of 2 is equal to 1, 0, 1. So this gi of 1 and gi of 2 is the sequences, generating sequences, or called as impulse responses. Generating sequences or impulse responses for this particular problem. So any doubts in this third and fourth? 3 and 4. Any doubts, put in chat box. Let me check it. Do not add, do modulo to addition. So for the answer for adding 3 bits for Tanuja, the answer is, how do we get x1? I'll write it in like this. x1, how do we get? M plus m1 plus m2, right? For example, x2 is m and m2. So then for x1, all the 3 bits are being present. So 1 into m1, I can rewrite it as 1 into m1 plus 1 into 1 into m plus 1 into m1 plus 1 into m2. So when we find the genetic sequences are only the values of those message bits. So for x1, the value will be having what? The value will be only 1, 1, 1. First is m1, m2. No, you didn't read the question properly. So first we need to find the dimension, then we need to find code rate, then we need to find the constraint length, then we need to find what is this? We need to find generating sequences, and after that, for a particular m or for a particular value of message, only we need to find output sequence. Okay, first see the diagram. So I'll show you the diagram again. I'll show you it. Can see in the diagram. Fifth one is a separate subdivision. In the diagram, they didn't give m is equal to 1, 0, 0, 1, 1. They had given only m. You can see output sequence. So till now we are having m is equal to only 1 bit. We will be finding what happens when m is equal to that value 1, 0, 0, 1, 1. If m is equal to 1, 0, 0, 1, 1, what is the output? That we need to see in section 5. Okay. You should not confuse with given question number 5. We are doing it in sequence. That we'll do. What happens when m is equal to that value? Okay. Till now we didn't give any specific m value, right? There is no specific m value till 4 till fourth section. fourth, there's no specific value of m till fourth subsection. Okay. So after this one, we are going to give m as a specific value, and let us see what happens. Okay. So now, I think then till subdivision of generating sequences is understood for all. So these generating sequences are also called as impulse responses. So now we are going to give this message sequence as in the question 1 0 0 1 1. So what is the output we'll see. Okay. So now to obtain the output sequence, we need to substitute the value of m. Okay, now here comes your value of m as you asked. So write the m0, m1, m2, m3, m4 values 1 0 0 1 1. The meaning is that m0 is 1, m1 is 0, m2 is 0, m3 is 1, m4 is 1. Okay. So now recall the xi of 1 equation. Okay, xi of 1, which is summation L is equal to 0 to m gl of 1 mi minus l. Okay, now we have to do this with iterations I is equal to 0, I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5, I is equal to 6. I is equal to 6 for x1. Similarly, we need to do it for I is equal to 0, I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5, I is equal to 6. Okay. So with I'll explain you the I is equal to 0 for the above equation. I is equal to 0. Substitute I is equal to 0 in this equation 3.5.11. We get x naught of 0, sorry, x of 0 of 1, which is L is equal to 0 to m gl of 1 m I is 0, so minus l. Okay. Now substitute this message. Substitute this message. So g naught of 1 into m naught. So g naught of 1, check whether it is present for this value. So you can see, refer the genetic sequence g naught of 1. You can see g naught of 1 is 1 always. So bring that here. M naught is 1. So substitute that here. Okay. M naught is 1. So substitute here. So we get g naught of 1 is equal to 1 and m naught is equal to 1 from this two equations. So which is 1 into 1 we get is equal to 1. X naught of 1. Similarly, I need to substitute I is equal to 1 in this above equation. If I substitute I is equal to 1, this in this equation I will be getting two terms. You can see we'll be getting two terms. One is g naught of 1 into m1, then modular addition g1 of 1 into m0. So this has to be done till we get m0 values. Okay, if I substitute I is equal to 1, this above equation, this will become x1 of 1, which is g naught of 1 into m of 1, modular to addition g1 of 1 into m0. Okay, so you can see that I is equal to 1, so m1 is there, and the subsequent decremental order of that m0 is there. Okay, decremental order of m0 is present. Then we'll get g naught of 1, which is known 1, m1, which is 0, you can write it here. Then 1, g1 of 1 is 1, m0, which is given is 1. So these two multiplied, we get 0, these two multiplied 1. So 0 modular to addition 1, we get 1. This is I is equal to 1. Next is I is equal to 2. So if I substitute I is equal to 2, I'll be getting three terms. You can see g naught of 1, g1 of 1, g2 of 1. G naught of 1 into m2, g1 of m into m1, g2 of 1 into m0. So substitute the equivalent values, we get 1. Simplify using modulo to addition. Similarly, do it for next I is equal to 3. We will get, if I is equal to 3, we will get these sequences. We will get these sequences. G naught of 1 into m3, modular to addition g1 of 1 into m2, modular to addition g2 of 1 into m1. Do substitute all the g naught of 1, g1 of 1, g2 of 1, and the particular m0, m1, m2. So we'll get this value. Then substitute I is equal to 4 in the above equation, we will get this. G naught of 1 into m4, g1 of 1 into m3, g2 of 1 into m2. Then simplify, substitute the values of g naught of 1, g1 of 1, g1 of g2 of 1. We'll get a value. Similarly for I is equal to 5. Substitute for I is equal to 5. G naught of 1 into, when you substitute 5, we'll get m5. Keep in mind we don't have m5. Don't have m5 at all. And we'll have m4. Okay, m4 will be there. So g1 of 1 into m4 plus g2 of 1 into m3. So only these two are available. So substitute that. Then do I is equal to 6. Do I is equal to 6, we'll get m6, which is not there. Then we'll have m5, which is also not there. So then we'll have only 1, g2 of 1 into m4. Since m6 and m5 are not available in the question, okay, since the messy bits are not available, we'll get only this values. So we'll get the value as something, some value we'll get. So now substitute, for example, I is equal to 7. If we substitute I is equal to 7, we'll get M7, M6, M5. We'll get that only. We'll get M7, M6, M5, which all the three are not available. If all the three are not available, we need to stop the substitution of I. Understood? Until we don't get these terms, we need to stop it. We need to stop it. So then I can write the output of the x1. So the output of the x1 can be written as in this sequence. So x naught of 1, which is 1, x1 of 1, which is 1, x2 of 1, which is 1, x3 of 1, which is 1, x4 of 1, which is 0, x5 of 0, which is 0, and this x6 of 1, which is 1. So I'll write it in sequence 1, 2, 3, 4, 5, 6, another one 7. Okay, so this would be the output of your x1. Similarly, we need to do it for x2. Substitute the I values in this formula. Substitute the I values in this formula. We get off everything in terms of 2. You can see that in the power it is in 2, bracket of 2. In here, everything is in bracket of 1. Why? Because the diagram is, the generated sequences for x1 is, everything is gi of 1. And the genetic sequences of x2 is, everything is g2 of 2. So substitute I is equal to 0, we will get, then substitute I is equal to 2, 3, 4, 5, 6. Substitute I is equal to 7 also, we will not get it. Okay. If substitute I is equal to 6, it will be till M4. We substitute till I is equal to 7, it will become M6, M7 and M5, so which is not valid or which are not available. So we'll get this sequence. So you can see 1, 2, 3, 4, 5, 6, 7. Do manipulation, then we'll get this answer for x2 or xi of 2. Now we need to write both of these two sequences to get the final output. So how do we write is that x0 of 1 and 2, x1 of 1 and 2, x2 of 1 and 2, x3 of 1 and 2, x4 of 1 and 2, x5 of 1 and 2, x6 of 1 and 2. So write it in pairs. Okay, write it in pairs. So x0 of 1, you can see what it is 1. So x0 of 2 is 1, so write it. So similarly, x1 of 1 is 1, so x1 of 2 is 0, so write it, comma for x2, then comma for x3, comma for x4, comma for x5 till x6. So this is the final output at xi, for this particular problem. So this is how to do output due to modulo 2 addition. This is a sequence. The thing is, you need to substitute the I value correctly. If you substitute the I value correctly, it will be easier. So any questions you can type in chat box. I'll give you 2 or 3 minutes for viewing this problem. You can have a go through. For queries, type in chat box. Though this convolutional coding seems to be somewhat complex in solving. Once solved, it will become easier, and this will detect and correct more errors as compared to the cyclic and linear block codes. So have a glance of this. Yes, what is one more problem? Yeah, no, we'll go for the next section and the next problem. This is the same. Okay. So far, what we had seen is the domain analysis in terms of time domain approach of convolution encoder. Now, after the time domain analysis, this is how to do time domain analysis. Next is transform domain analysis. Okay, so the transform domain analysis will solve another problem which would be somewhat easier in solving as an manipulator. Okay. As a manipulator, this would be easier as compared to that. It is transform domain analysis. For every section, we have only one problem to be solved due to time constraint. One more problem. Okay, you will understand if you solve this next problem. Don't worry. Okay. Now we'll see transform domain. Okay, if you see transform domain, you will feel time domain to be as uh, easier. Okay, we'll see that. So the transform domain approach for analyzing the convolutional encoder is that it would be a similar procedure but with some modifications. So we had seen in the previous that the convolution of generating sequence and message sequences takes place. They are being calculated by simply by applying transformation to the sequences. So where it changes is that it changes only in the pattern of writing the polynomials. So where do we write the polynomials is that in the generating sequences. So let the impulse responses be represented by this polynomials. For example, instead of writing, you can see here in the time domain approach, we had wrote only in terms of message bits G0 of 1, G1 of 1, G2 of 1, G till GM of 1. Similarly, for second order or the X2, we wrote G0 of 2, G1 of 2, G2 of 2 till GM of 2. But in transform domain, what we are going to do is those bit sequences that are being obtained, we are going to convert them into polynomials. If you convert them into polynomials, it will be easier for us to manipulate. Okay, so for x1 we can write the generating sequences in terms of polynomials as g1 of p in general, which can be expanded to g0 of 1 plus g1 of 1 into p power 1 plus g2 of 1 into p power 2 plus g3 of 1 plus p power 3 till gm of 1 into p power n. Similarly, we can write in terms of second generating sequences g2 of p is equal to g0 of 2 plus g1 of 2 into p plus g2 of 2 into p square plus g3 of 2 into p power 3, and it goes until gm of 2 into p power n. So then for message also we can write in terms of polynomials. So m of p is equal to m naught into p power naught plus m1 p power 1 plus m2 p power 2 plus m3 p power 3 till ml minus 1 p power l minus 1. So this is your message polynomial. This is your message polynomial. So now a new term is introduced, which is L. So L is the length of the message sequence. Okay, L is the length of the message sequence. So the convolution sums. How do we do convolution? Is that the convolution sums are converted to polynomial multiplications in the transform domain. Okay, convolution sums are converted to polynomial multiplications in the transform domain. So though you did not understand, for example, if you didn't understand the time domain, try to understand the transform domain, because this transform domain, same concept is your time domain. With here in transform domain, we'll be doing it with polynomials, there without polynomials. So that's all. That is the difference. Okay. So x1 of p will be g1 of p into m of p, and x2 of p will be g2 of p into m of p. So see here the message m of p is same. So whereas in this also, can see the generalized equation. Here we wrote message in terms of m0, m1, m2 till mm. In transform domain, we are writing in terms of polynomials m0 of p, m1 of p, m2 of p, m3 of p, and till. Okay, so that. So when you find the x2 or x1, see here, we are finding x1, we are finding x2. What it is? Summation L is equal to 0 to m, where L is greater than I. Okay, g of 1 into m of I minus L. x2 is summation L is equal to 0 to m, gl of 2 m I minus L. So these two equations keep in mind. So that in terms of transform domain, we are writing in polynomials. So that is difference. x1 of p is equal to g1 of p into m of p. x2 of p is equal to g2 of p into m of p. Okay. So these two equations are the output polynomials of sequences xi of 1 and xi of 2. And keep in mind that all the convolution that is being done are being done by modulo 2 addition. Okay. We'll take the same example. We'll take the same example. Just now we had seen, right? So the same example. The same example we are going to take, except for the fifth part. Remaining all will be same. Okay. Except for the fifth part, remaining all will be same. So in the fifth part, we are going to analyze this output sequence for message sequence of m is equal to some value in terms of time domain we had done now. So in terms of transform domain, we'll do it. Okay. So that is the question. So repeat part 5 of example 3.5.1 using transform domain calculations or polynomial multiplications. Okay. So for that we need to recall the gi of 1, which is 1, 1, 1. Recall it. Recall that. So g 1 of p can be written as, since all the three are present, see here, all the three are present, we can write the polynomial of that as 1 plus p power 2 with the generalized formula that we had seen in cyclic codes. So 1 plus p power 2, and that too of gi of 2. So gi of 2 we are familiar, right? gi of 2 in that problem we had got 101. So 101. So which is 1 plus p power 2. So 1 plus p power 2. Next, write the given message. So we'll take the same message. M is equal to 1, 0, 0, 1, 1. So write it as it is. Write as it is. So find for this also m of p. So for this message sequence, m is equal to 1, 0, 0, 1, 1. Find the polynomial. So when I find the polynomial, it will be 1 for this 0, 0. So we have p power 3 plus p power 4. Because the order is m0, m1, m2, m3, m4 per message. So we had got this m of p. Now, what we are going to do is we are going to determine the output due to adder 1. We are going to determine the output due to adder 1 for this problem. Okay. Adder 1 output is what? In transform domain, adder 1 output is x1 of p. x1 of p is g1 of p into m of p. So we know g1 of p. What is g1 of p? g1 of p is 1 plus p power 2. So write it. Then next we know m of p. M of p is given in the messages 1, 0, 0, 1, 1. So write 1, 0, 0, 1, 1s. equivalent polynomial. So 1 plus p power 3 plus p power 4. So write it. Now simplify. Now simplify it. You know simplification, right? 1 into everything, you get 1. So 1 into 1, you get 1. 1 into p power 3 will be there. 1 into p power 4 will be there. Then p into 1, p into p power 3, p into p power 4. Then p power 2 into p power 3, p power 2 into p power 3, p power 2 into p power 4. All when you simplify, you will get 1 plus p power 2 plus p power 3 plus p power 6. We will get this. So for this, write the equivalent sequences. So 1 is there. So write 1. P power 1 is there. So 1. P power 2 is present. So 1. P power 3 is present. So 1. P power 4 and P power 5 are in absent, is not there. So P power 4 and P power 5 will be 0, 0. So P power 6 is there. So write 1. So we got the output due to adder 1. Similarly, we are going to do it for adder 2. Adder 2 output is x2 of p. So x2 of p is g2 of p into m of p. g2 of p into m of p. So g2 of p, kidhar hai? Yeah, it is here. g2 of p is here. So 1 plus p power 2. So 1 plus p power 2. So write it here. M of p, just now we wrote somewhere. So yeah, m of p is equation 3.5.19. 1 plus p power 3 plus p power 4. So write it here. So now manipulate. Do manipulation. So we get 1 plus p power 2 plus p power 3 plus p power 4 plus p power 5 plus p power 6. And find the equivalent x2 of p, which is 1 0 1 1 1. You will get like this. Now after finding this, find the output sequence x of xi. Xi will be in the sequence. Just a minute, I'll show you. Xi will be in the sequence x0 of 1, x0 of 2, x1 of 1, x1 of 2, x2 of 1, x2 of 2, x3 of 1, x3 of 2, x4 of 1, x4 of 2, xy of 1, xy of 2, x6 of 1, x6 of 2. So like this you should write, as we had done in the previous. So we get here also the output sequences. You need to write in the 0th place whatever is present in pairs. One place in pairs. So differentiated by comma. So 1 1 comma 1 0 comma 1 1 comma 1 1 comma 0 1 comma 0 1 comma 1 1. So when you compare this with the previous time domain analysis, you can see this x of I, which is obtained by time domain, is same as we had done with the transform domain. And we need to make a note that there are only very few manipulations are involved in transform domain. Very few manipulations. You could have seen this. You could have seen the time taken for manipulating, as I had explained you, for time domain and transform domain. Okay. There we won't use polynomials. We'll use the each and every bit sequences. Here we'll be using the corresponding messages polynomial. So now you have to decide in what way you have to use, or in what domain you need to determine the convolutional coding. So any queries in this? If anything is there, put in the chat box. The transform domain analysis is very much simpler than the time domain analysis. The same problem we have done, right? We have taken that only the fifth part. We have done the fifth part there and fifth part here. You can see when we use a polynomial, the manipulations are very few. So you have to decide which one is the best method for you to solve any problem. Okay. Either time domain or transform domain. Let me check in the chat box for any queries. Yeah, for Srikala's one more problem explanation, I'll send you a different problem for time domain analysis. Don't worry, I'll send you in WhatsApp or I'll send you in what do you call, through your Google Classroom. I'll send you another problem with, I think, with a better explanation I'll give you. Don't worry. I think now you would have understood whether time domain analysis or transform domain analysis is best. Okay, so I'll proceed further. So to see the next topic or go for the next topic with the same type of convolutional encoder, we are going to see three different concepts. Okay, same k is equal to capital K is equal to 3, small k is equal to 1, and n is equal to 2. Same combination we'll take and we'll study the operation of a convolutional encoder with some other methodology called code trellis, code tree, and state diagram. So when you hear this, I think most probably you would have heard about state diagrams in your digital system design or your digital electronics. The new term would be your code tree and trellis diagram. Okay, don't worry, those are not that much big as you think. Those are very, very simple in convolution. Okay, you can see the diagram, check whether the same diagram is that the same diagram that we had done in the previous example problem and in the previous convolutional introduction. You can see we have capital K is equal to 3, so 3 shifts. Okay, 3 shifts, M, M1, M2, message input bits M. Okay, which is the current message bit M, small m. And we have flip-flops M1 and M2, which are the 2 bits representing state of the shift registers. And see X1. X1 is obtained due to M, M1, M2. You can see X1 is obtained due to M, M1, M2. So we'll get X1 of P or Xi of L. We'll get it. In the case of time domain analysis, it is I. In the case of transform domain, it is P, polynomial. So X2 will get, it is in terms of M and M2. M, M, and M2. So there we can find X2 of P, a transform domain, or X2 of I in the case of time domain. So then we have the output, regular output as same. So it is given to the output. So make sure that the diagram is same. I'll go back and I'll show you the same again also if required for better understanding. You can see that the problem that we are redrawn is also the same. X1 is due to M, M1, M2. X2 is due to M and M2 in this problem. And the same that we had defined for capital K is equal to 3 and small k is equal to 1 and n is equal to 2. You can see that the same X1 is due to M, M1, M2. x2 is m and m2. So the same representation of convolutional encoder we are going to take for this topic. Okay. So diagram is same. So next go to the next. So states of the encoder. We are going to define states of some encoders. So what we are going to see is that we are going to define the states. Now, how we are going to define the states is that we are having shift registers M1 and M2. So since there are two shift registers, we'll be having maximum possible combinations as 4. Since we are dealing with binaries, so I can have M1 and M2 as 00 or 01 or 10 or 11. So totally there will be 4 states. So these 4 states we are going to draw in terms of state diagram. Okay, so that we call it as states of encoder. Simple logic, M1 and M2 we are writing in a table. So M2, M1 we are writing in a table. We are giving the different input combinations. So 00, 01, 10, 11. Keep in remembrance, first one is M2, second one is M1. And for 00 we are assigning a state encoder, some label, so which is A. A is the label. For 01 we are labeling B, small b. Everything is small. For 10 we are labeling it as small c. For 11 we are labeling it as small d. So this is how to assign states for the encoder. So after assigning, we need to develop the states. Okay, so which is a part of a development of code tree. So we need to form a tree based upon this states. So based upon these states, we need to form a tree. So how do you form a tree? Is that it's a simple, but the thing is we need to implement it properly. So let us consider initially for the convolutional encoder, the message, some message is given. Okay, we consider a message called m is equal to 110. 110 is being given. Okay, consider message sequence m is equal to 110 is given, and the state which is being present in m1 and m2 will be always 00 initially. Initially you can see that the initial values which are being stored in m1 and m2 in this diagram, m1 and m2 in this diagram is always 00. Okay, always 00. Okay. M1 and M2 will be always 00 initially. So now I am sending the first bit. I am sending the first bit to this block diagram. So if I send the first bit to the block diagram, first of all I should write what is x1. Before sending I should write what is x1. So x1 is due to m, m1, m2. x2 is due to m and m2. So keeping that in mind, x1 is m, m1, m2. So see this left side block is there, right? Left side block. So m1 and m2 is 00. M is the first bit which I am sending here in message m is 110. So this one. So x1 I'll get modulo 2 addition of all the three. So 1, 0, 0. We get it as 1. For x2 I'll be doing modulo 2 addition of m and m2. So this first bit and last bit. So m and m2. Okay. So we'll get x2 is equal to 1. So when current message bit m is equal to 1, the x1 and x2 will be 1, 1. Will be x1 and x2 will be 1, 1. So this 1, 1 is transmitted to the output. And the register contents and the register contents are shifted to right by 1 bit position. Register contents are shifted to 1 bit position towards right side. So whatever is there, it will be shifted towards right hand side, 1 bit. So before shift, this would be your value in left hand side. So after shift, in the right hand side, a diagram is there, right? You can see right side block. So M will be present. M1, keep in mind this is not cyclic. Keep in mind this is not cyclic. So when I do right hand shift, so this one will come to this 0 will come to this, and this 0 will go out. So this 0 bit which is coming out will be discarded. Okay, so this will be discarded. Okay, so this bit will be discarded. So keep that in mind. So x1 x2 is 1 1 now. So now see the states. See the states. M1 and M2 is 1 0. M1 and M2 is 1 0. So M1 and M2 is what? M1 is 1, M2 is 0. So the state changes to state of encoder as B. Okay. So initially M1 and M2 were 0 0. So we had A. Now after giving M value, it has shifted to M is equal to 1 and B is equal to, sorry, M is equal to 1 and M2 is equal to 0, which is state of B. So that I'll explain you. This diagram I'll explain you. All right. So now we had sent only M is equal to 1. The first bit is sent. Next we should send the second bit. So what is the second bit? Second bit is M is equal to 1 again. Okay. Now let us send this second message bit 1 to the shift register. What will happen? Okay, let us see what happens. Okay. So when I send the second bit, already we are having M1 is equal to 1 and M2 is equal to 0. So see here in this block diagram, we have having this M1 is equal to 1, M2 is equal to 0. So in that we are sending M is equal to 1. So when I substitute 1, we should write what is x1? X1 is modulo 2 addition of all the three. So 1, 1, 0, we get 0. X2 is modulo 2 addition of M and M2. M and M2, we get 1 modulo 2 addition, 0, we get 1. So the values of x1 and x2 will be 0, 1. 0, 1, 0 and 1. Okay. And these are being transmitted to the output, and the register contents are shifted to right by 1 bit. Okay. They are being shifted to right by 1 bit. Okay. When we do right bit shifting, so this M2, whichever is present, will be discarded. So before shifting, it will be 1 1 0. After shifting, it will be M 1 1. Okay, you can see here. Now, what we are going to do? We are going to send the third bit. So the third bit is 0. So third bit is 0. So put 0 here. Okay. When we put 0, what will happen? We'll get x1 value and we will get x2 values. By doing modulo 2 addition, we will get x1 value as 0 and x2 value as 1. So we will get the x1 x2 value as 0 1. 0 1. So after completing all these three steps, what we are going to do is that we are going to see that what is the value of 1 1 in M1 and M2 that we are getting. So M1 and M2 is 1 1, so which is D. Okay, which is D. And similarly, when we go for third bit, sending of third bit M is equal to 0, we see that the value of M2 and M1 is 1 0. Probably can see that it is 1 0. Yes, when you do right shifting, it will become 1 0. So which is the state of C? Okay, you can see that state of C, and refer that here also you can see that state of C. M1 will be 0, M2 will be 1, so state of C will appear. So with this, all these things, we'll be drawing a complete code tree. Okay, we'll draw a complete code tree. Okay, so any doubts till this? Any doubts in doing these 3 steps in developing the code tree? Any doubts? If you have any doubts, put in chat box. Any doubts in this development of the code tree? Why? Because after the development, directly I will draw the code tree diagram. Any doubts you can put in chat box. Let me see. Not Harshvardhan. Nobody joined the class, huh? Exactly at 3:40 you're joining.
The network slow, sir. Before only join, now automatically takes it.
Automatically it is sending you out, huh?
Sir, it's showing someone has removed you like that.
No one will remove you. Only I am the controller. No one will remove you. I will send you the attendance today. You will see. At what time you joined, I can able to get you. I'll check and I'll tell you. At what time you joined the class, at what time you left, who removed you, who did not remove you, all I'll send you. Okay, let us see. So any doubts in this development of the code tree? Because a small uh, misplacing of values also will lead to a heavy errors in development of the tree. So that's what I'm asking you again and again. Any doubts in development of the tree? You should write the values of M1 and M2 correctly. How you assign ABCD for M1 and M2? In the same way, we should rewrite also, or we should able to interpret which one is given for A, which one is given for B, which one is given for C and D. Then only you can draw the code diagram, code release diagram, the state diagram correctly, or else it will become very wrong. In some places, you need to write in the sequence of M, M1, M2. In some places, you need to write the sequence of M2, M1. So make sure if that is done correctly, and if you're interpreting it correctly, then the problem will be easier. Okay, so let me move on to the next. Yeah, this is it. This is the analysis of the convolutional encoder for drawing code tree. Okay, for drawing the code tree. So first I'll explain the first one. So we are dividing it into 3. Why we are dividing into 3 is that we are having message bits, 3 message bits, 1, 1, 0. We are having 3 message bits. So I divided into 3 rows. Okay. So when I send message bit m is equal to 1, what will happen? So already the status of the shift register is 00, which is A. In encoder it is small a. I give 1. I give 1 to that. Okay, I give 1. So what happens is that x1 will be 1, x2 will be 1. X1 will be 1 and x2 will be 1. So then what happens is that I am making a right shift. Making a right shift by 1 bit. So this 0 will go out. Remaining will be in the place of m1 1 and in the place of m2 0. So this we are going to bring. Okay, this 1 0 is this encoder state B. Okay, this is the encoder state B. Okay, now here you can see this value of m2 and m1 in the row 1. See in the row 1, m2 is 0, m1 is 1. So that is B state. Okay, B state. So the transmitted outputs will be 1 1. So the transmitted output bits means the x1 and x2. So x1 and x2 is 1 1. So how do I draw this diagram? How do I draw this diagram? How do I draw the code diagram for this is that I start with A. So A is your 0 0. So state is 0 0. So when I give 1 for that, input message bit is 1. Input bit is message 1. I get a state. I get a new state. Probably saying a state, I get a new state, which is B. You can see that 0 0 is there for m1 and m2. I give message bit 1. The output is 1 1. And due to this, I do a right shift registering. I do a right shift of 1 bit and I get a new state. So that new state is 0 1. So that new state that is being obtained is small b, which I had assigned small b. So for A, which is 0 0, if I give a input message bit as 1, input message bit as 1, the next state is B and the output is 1 1. Okay, output is 1 1. So this is the code tree diagram for the first row. Okay, and always when input message bit m is given as 1, the arrow mark should be in bottom. We should draw a downward arrow. So downward arrow means mean message bit is 1. Okay, mean message bit is 1. So after the first row, in the second row, I have a state, the new state which is being generated. The new state is 0 1 for m2 m1. So m2 is 0, m1 is 1. So for this I am going to give a message m. M is 1, so 1 I write it here. So when I give 1 having B state, the outputs are x1 and x2, which is 0 1. Outputs are 0 1. Okay, x1 x2 is 0 1. So I do a right shifting by 1 bit. So the last bit will be discarded, remaining will be 1 1. So this 1 1 is your new state, which is D. It is D. Output bits are x1 x2 0 1. So from here, so already we are drawn from the start to A to B. So in B, if B is present, in B I am going to give what message input? I am going to give M message input. So M is equal to 1. So downward direction. So M is equal to 1. I get a new state as D, which is 1 1. With an output, transmitted output is 0 1. So write 0 1 here. So this is the code tree for M is equal to 1 1. Code tree for M is equal to 1 1. Already 1 we had sent the first bit. The second bit I am sending second one. So 1 1. So now I am going to send third message bit, which is 0. So when I send 0, the already existing M2, M1, which is 1, 1 of D state. So 1, 1 of D state. Okay. I'm going to give 0 for that. So if I give 0, the output will be 0, 1. X1, X2, output, transmitted outputs are 0, 1. Then I do right shift in the register. I do a right shift. So when I do right shift, the last one will get discarded, remaining will be 0, 1. Okay, M1 0, M2 1. So which is C. So the new state will be C having M2 1, M1 0. So here is my point now. So D is my point. So from D, I'm giving message input M as 0. So it should go in upward direction. So I draw it in upwards. So upward arrow mark means message bit is 0. Okay, so it goes in upwards. So what is my output? Output is 0, 1. So 0, 1, I'm writing it here. What is the next state? Next state is new state that is obtained is C. So it goes to C. So starts from A and ends with C. So this is the analysis of this convolution encoder. A small representation of code tree. Okay. So now only I'm going to draw an actual code tree. Now only I'm going to draw an actual code tree. Okay. What I'm going to draw in this actual code tree is that in the previous analysis of the given problem, I did not substitute. You can see for the given problem it was 110. Okay, 110. Zero zero, it is A. States A is equal to 0 0, states B is equal to 0 1, state C is equal to 1 0, state D is equal to 1 1. With outputs, I am writing it here in pencil. You can see left side. X1 is obtained due to M, M1, M2. X2 is obtained due to M and M2. So simply I am applying M is equal to 0 to A state. What will happen? It will produce A again. And if I substitute M is equal to 1, I'll get B state. Then further I'll be in it again. If I give again A state, somebody just now joined the class. I'm unable to predict who is it. Okay, I'll find out that also. Okay. So again, when I substitute for this A 0, I'll get again A state. And I need to substitute again 0 for this A state. For this A state, if I substitute M is equal to 0, I'll get again A. Okay, so 3 times. So 3 times if you do, you go this. So and for this A I'll go for. Okay, or this A, I'll get again A. So when For every m is equal to 0 in A, we get A state or B state only. You can see here A state or B state. Okay. And here, when I substitute for B, you can see when I substitute for B is equal to 0 or 1, keeping the first one as it is, first bit as it is. When I substitute 0 or 1, 0 in the sense it goes in upward direction. So if I substitute 0, I get C. If I substitute 1, it goes to D. Okay. I should do it for 3 cases. Why? Because we are having capital K is equal to 3. So 3 shifts. So 1, 2, 3 shifts. So 1, 2, 3 shifts. So here also 1, 2, 3 shifts. Okay. And similarly, when I substitute for B, here in the upper, we get what is in upper. Upper is your 0. So if I substitute 0, I get C. If I substitute 1, I'll get D. And similarly, now I should see for C. So for C, if I substitute 0, it gives A. And if for C, if I substitute 1, it gives B. Okay. So similarly, I need to perform till the last. Only 3 times shifting. Okay. For 3 shifts, I should perform 3 times. And I need to write the appropriate outputs, what we had got. Okay. So this portion indicates that it is a repetition of the code tree. So the same, whatever I got here will be a repeated. Okay. So this is the code tree for the convolutional encoder. So next is, let me check. Next, in a short time, I'll finish the code trellis. Okay. So next, how to draw the code trellis? It's very much simple. So here, the code tree is, from the code tree, we are going to derive the code trellis. In a short manner, I'll tell you. So this darkened line represents 0. So when I draw in dark, it is 0. When I draw it in dots, it is 1. The meaning is that m is equal to 0 or m is equal to 1. Okay. So in the current state, write 4 states, A, B, C, D, equivalent encoder values that I had given 0, 0, 0, 1, 1, 0, 1, 1. Similarly, for the next states, we also got 4 states. A is equal to 0, 0, B is equal to 0, 1, C is equal to 1, 0, D is equal to 1, 1. So write in the next states also. So how do I draw the code trellis? Is that, see, if for A, if I give 0, which is in dark line, what I got another state again. As for A, if I give 0, I got A itself. So connect this A to A in dark if m is equal to 0. I think you would have understood this. So if I give m is equal to 1, small m is equal to 1, which is in dotted lines. If I give m is equal to 1, so what happens? I got B with output 1, 1. So output 1, 1. So write the output as 1, 1 here. In the transition, output is 1, 1. And for A to A, the output is 0, 0. I forgot to say. Okay. So this is your code tree for A. Similarly for B, I need to see. For B, when I give m is equal to 0, I got C. So connect that with the output as 1, 0. And for B, I am giving m is equal to 1 in dotted. M is equal to 1, which is in dotted. The output is 0, 1. So right. And what is the next state? Next state goes to D. Similarly for C, if I give m is equal to 0, the output is 1, 1 and it goes to A state. And for current state C, if I give m is equal to 1, which is in dotted lines, it gives B, which is 0 1 and the output is 0 0. So write it. Similarly for D, if m is equal to 0, connect it in dark line, which is 0 1. So 0 1. Output is 0 1. Next state is C. Similarly for D, if I give m is equal to 1, it goes to again D state, which is 1 1. Okay, again 1 1. So this is how to draw the code trellis of the given convolutional encoder. Next is the state diagram. I think most probably everyone are familiar with state diagrams, right? We can combine the current states and the next states with the help of state diagram. So put 4 states A, B, C, D. Dotted lines are representing the same. Dotted lines are 1 and dotted lines are 1, dashed lines are 0. Okay, so accordingly you can draw the state diagram also. Okay, here is a comparison of the code tree and the trellis diagram. The code tree indicates flow of coded signal along the nodes of the tree, whereas trellis diagram indicates transitions from current to next states. Code tree is lengthy way of representing coding process, whereas code trellis diagram is shorter way or compact way of representing coding process. From the diagram itself, you would have understood. Decoding is very simple using code tree, but in trellis diagram, it is a little bit complex using trellis diagram. In code tree, the repetition of stages in the encoder is done, whereas in trellis diagram, repeats it in every state, and in trellis diagram, it has only one stage. In code tree, is complex to implement in programming, whereas trellis diagram is simpler to implement in programming. When you implement this in a program, it will be very easier for trellis diagram. So these are the difference between code tree and trellis diagram. So, any doubts? Any doubts in this presentation? You can put in chat box or you can send me in WhatsApp since it's time out. In the next class, we'll start the next topic of convolutional codes. Okay. Any queries? There are still 2 or 3 minutes. You can put in chat box. If you are familiar with m is equal to 0, what to do? M is equal to 1, what to do? Then the concept of convolutional encoding in determining this table. This table, yeah. If you're able to do this table correctly, everything is easier. Only decoding this table is a bit complex. So if this is done, easily we can get the code tree, easily we can get the code trellis. And you can draw the state diagram also. Present state and the next state, depending upon inputs. Okay, if there are no queries, you can leave the meeting.
Attendance, sir.
Attendance I had taken.
Okay, sir.
I need to find who all are late. That's all. You can leave the meeting. Thank you all.